Viewers, my name is Xiaochen. I'm an assistant professor at the University of Florida and also a Nelms member. I'm very honored to present at the Nelms Lightning Talk series. The topic I'm introducing today is online monitoring of big data streams in IoT systems, where I will share my research interests and experiences for big data analytics for IoT. The motivation of this series of research work lies in the sensor technology development in IoT systems, such that the information we typically acquire from IoT systems are large volume and high dimensional. And we rely on such big data to make online monitoring decisions. Here are some examples. The first example is in environmental monitoring. Practitioners deploy very large seismic sensor networks these days to monitor earthquakes. Because of the very large size of the sensor networks, the energy is actually, it consumes a large quantity of energy, and which makes the energy cost very expensive. So if we turn on all the sensors at the same time, it actually requires the managers of this network to replace the batteries quite often, such that we cannot really afford this much of sensors working at the same time to acquire this big data sets. So naturally, we would think about which subset of sensors we want to turn on and dynamically change the sampling layout, the layout of the sensors in real time, depending on the online observations, because the earthquake is actually a very rare event. The second example is in UAVs applied in search and rescue. The number of UAVs we typically have is very limited, but we want these UAVs to cover a very large area by deriving these UAVs around the area. So in this case, which location we want the UAVs to monitor at the next time becomes very important, as effective algorithms to direct the UAVs will result in very different performances in quick search and rescue. In the third example, we talk about image sensing. NASA practitioners place optical cameras on the satellite to take pictures at the surface of the sun. At each second, tons of such solar images will be generated and transmitted back to Earth for analysis. And the objective here is to detect earthquakes. However, the communication between satellite and the Earth is actually very limited, such that not all of these images can be transmitted back. Therefore, which pixels that we want to process for quick solar flare detection is a very interesting and important research question. So in all of these applications here, we are required to quickly detect abnormalities in a complex system. However, they all face the same problem that the resource is very limited in these systems. And how do we adaptively determine the most informative data and observe is very important. Now I will share how this problem is formulated and assumptions are made in the current literature. So we typically assume that there are p variables that are measured at the same time. So the p variables could be different components of IoT system. For example, in the solar flare occurrence problem, each variable could be 1 pixel of the image. And because of the resource constraint, only R out of the p variables can be observed at each time t, where we denote as the XOT, the observable data sets. When the process is in control, so no abnormalities are there in the system, we assume that in control mean it's 0. This can be achieved by pre-centering of all the data with some preliminary analysis on the mean of the data streams. And at a certain, at some unknown time tau, we assume that there is a abnormality such that the mean of the process is not zero anymore, and we don't know the number of affected variables in practice. So now the question becomes, how do we monitor such big data sets with only R variables observed and make quick and correct monitoring decisions? So in this talk, I will focus on one of my recent papers and introduce how data augmentation is applied in these research problems. Traditionally, when we are monitoring the system status, we typically only rely on the observable variables to make the decision. However, we know that there could be so many unknown variables because either resource limitation or natural unobservability of the system. But if we can actually infer the relationships between the observable and unobservable variables, they can help us jointly infer the system status, which makes the monitoring more reliable and informative. This idea actually has been discussed in other applications previously, which is called data augmentation. So data augmentation is naturally the methods via introduction of unobservable variables or latent variables. They are applied in such as design of experiments, regression, multi-follow simulation, but not all of them. But they are not actually not a lot of methods applied in monitoring. In online monitoring, anomaly detection. So the proposed method here is actually based on augmentation of anti-ranks. The idea is that the anti-rank here is actually a non-parametric method. We don't impose any distributional assumptions on the data streams, which will make the method more robust. So we are testing the null hypothesis that whether all the data streams are in control, and by assuming there's a sparse change in the system such that only like very small number of variables are abnormal, we can actually use Bayesian statistics to determine what is the expected anti-rank indicator given the observable data streams. And these would be the results of the augmentation. So based on these statistics here, there are the major steps we will take for the monitoring. So first we propose, this is the augmented vector that we propose based on the data augmentation. And ST2 here behaves like the expectation of ST1. And then we propose a monitoring statistic YT, which measures the differences between S1 and ST. If S1 is far away from its in-control expectation, we say that the process is abnormal, stop the monitoring process. Otherwise, if we didn't trigger an alarm, we will have to reallocate the monitoring resource every time step, depending on ST1, which is the augmented statistic that we have. This is because the ST1 here is actually our stream informativity of whether each data stream are worth sampling. I will give an illustration here using 4 variables, which is a toy example that shows the strengths. So here are the measurements of the 4 variables here, and the CSI here shows on the table on the right-hand side shows how our data is augmented. So if the background of the data stream is green, that means these variables are being observed right now. And we have 2 unobservable ones as well here. So at the beginning, when the process is in control, you can see that all the axes have normal observations, and their augmented vectors are also appear to be not that extreme. And the monitoring resources are actually allocating around all these variables such that no variables are left unattended. However, at time 6, X3 has the out of control shift. So it has a mean shift. And we can see that since then, when this variable is observed here, it would actually result in a very, very suspicious augmented data, such that our monitoring resources will stick to this variable and observe. And this will allow us to identify this variable as the abnormal variable as well. We can theoretically show two properties of the proposed algorithm. The first one, we call it the in-control property because it studies the in-control case. This property tells us that if the process is in control, actually, the monitoring resources will be redistributed to each variable with infinite number of times, such that no variables will be left unattended. This is a very desired property because although we have very limited resources, we hope that these resources could sequentially cover all components in an IoT system, such that no matter where the problem occurs in an IoT system, we can detect it, right? I'll skip the proofs here. The second property here is the out of control property. This one tells us that when there is actually a shift, and when the mean shift is big enough, we can actually show that there is a non-zero probability that the out of control variable will be kept observed forever, which means that the sensor resources or monitoring resources will eventually stick to the variables with large mean shifts. This property will ensure that abnormalities in a system will be detected quickly. I'll skip all those simulation studies and show a case study, real case study instead. As we mentioned in the introduction, solar flare here is actually a abrupt explosion at the surface of the sun, and such an explosion is hazardous to spacecraft, satellites, and astronauts in the space, as well as terrestrial facilities like electrical grids. So it is preferred that we can detect solar flares ahead of time, such that we can take reactions. The data we use for the solar flare occurrence is the solar images that is 232 times 146. And in total, we would have more than 30,000 variables in total. So this is kind of very big data, actually, considering the communication bandwidth between the Earth and the Sun. And we try to detect such solar flares using only partial observations. And these are actually the results of our proposed methods and the benchmark existing methods. So you can see that with our methods, we can actually detect the occurrence way faster than the existing ones. And we can show that our method is robust when the number of observable variables is small. So that means if we have a more strict, more serious resource limitation, our method would perform very robust. And the next figure might tell you why. So here on the left, we have the original solar images in control and out of control. So we can see an apparent out of control shift here, a solar flare occurrence. Using our augmented vector, we can automatically, the entire augmented vector would be very, very different with the in control ones, because the augmented vector actually changes with the changes with the online online data. So the entire image, the data stream here will change with the online observations. However, for existing study, only observable variables at this changed abnormal data streams here will have a change, which will result in slower detection. All right, so this is a quick talk about some of my research interests and questions. I really appreciate you watching this video. And if you have any interest talking with me, or if you want to know more or read the papers, feel free to let me know. Thank you so much.